Hello my dear student, welcome to EPG Pathshala. I am Anchal Srivastava from Department of Physics, Institute of Science, Banaras Hindu University. Today we are going to discuss about the module Magnetic Tunnel Junction MTJ under the paper Nanoscience and Technology 2. After completing this module, the student will be able to learn the basics of magnetic tunnel junction or MTJ, or nanostructure device within the field of magnetoelectronics or spin electronics and spintronics. We will learn about the tunnel magnetoresistance TMR and how this is a magnetoresistive effect that occurs in the magnetic tunnel junction, which is MTJ. We will learn about the basic phenomena in MTJ and learn about the development, the coherent spin tunneling, and what are the future perspective of MTJ. We'll also learn the coherent spin tunneling and what are the future perspective of MTJ. In the early 1990s, high magnetoresistance MR was discovered for magnetic tunnel junction MTJ material. MTJ material is made up of at least two magnetic layers separated by an insulating tunnel barrier. In the MTJ, the current flows perpendicular to the film plane. The best results have been achieved with aluminum oxide tunnel barrier. Since the initial experiment discovery of MTJ material with promising MR, the techniques of producing these materials as well as key properties has been dramatically improved. Tunneling MR values are in the 20 to 50% range. Instead of using inorganic insulating barrier layers like aluminum oxide, attempts have also been made to insert organic insulating layers to make MTJ devices. This can also lead to the fabrication of flexible organic devices in future. The electronic devices with typical dimensions of few nanometers in either of three directions display not just the miniaturization but unique properties not known over last 5 to 6 decades since the beginning of solid state devices. Single electron transistor, spin valves, and magnetic tunnel junction are conceptually new devices based on nanotechnology. Such devices are fast, compact, relatively cheap, and finding their way to market. Spin valve type devices are already being used in personal computer to read disk, which have enabled to increase data storage capacity of hard disks. Interestingly, a spin valve and MTJ are based on a concept which itself is growing into an area in itself known as spintronics or spin-based electronics or magnetoelectronics. It is well understood that an electron or hole has both charge and spin. However, electronics has so far used only the charge properties of electron or hole, and spin has been neglected. It has been now realized in recent years that if a spin of an electron or hole is taken into account properly, fabricated device would lead to some superior devices. Using an external magnetic field, a spin transport can be controlled. Advantage with the spin is that it cannot be easily destroyed by scattering from collisions with other charges, impurities, or defects. Many spin-based devices like spin FET, spin LED, spin RTD, optical switches with terahertz frequency, modulators, encoders, decoders, and qubits for quantum computers are on the hot list of scientists and the technologists. We consider here devices based on giant magnetoresistance, a spin wall, magneto-tunnel junction, which is MTJ, magnetic tunnel junction, which is known as MTZ. In the early 1990s, high magnetoresistance, known as MR, was discovered for magnetic tunnel junction, which is MTJ material. This magnetic tunnel junction material is made of at least two magnetic layers separated by an insulating tunnel barrier. The current flows perpendicular to the film. This has been shown in figure. The best result have been achieved with aluminum oxide tunnel barriers. Magnetic spin wall and magnetic tunnel junction using nanomaterials or some other high-speed devices which are the products of nanotechnology. Spin wall type devices are already being used in personal computers to read disk, which has enables to increase data storage capacity of a hard disk. Advantage with spin is that it cannot be easily destroyed by scattering from collisions with other charges, impurities, or defects. Let us discuss the magnetic tunnel junction and Moore's law. Around 1959, James Moore predicted that there would be a reduction in the transistor size with time. Even since it depicted the trend in miniaturization of electronic devices has faithfully followed what is known as Moore's law. It implies that every 18 months the reduction in the size doubles, or the number of transistors on the chip doubles, or the processing powers of computer doubles. However, following this law, the device has reached now a lowest size of 100 nanometer, and deviation from the law has begun. It is now only increasingly difficult to achieve smaller and smaller size, less than 100 nanometer, but also difficult to retain linear nature of the graph that Moore has predicted. Below a size of 100 nanometer, we know that beside the surface effect, materials also have size-dependent properties. Therefore, nano device using active or passive nano components cannot be expected to behave like those of large micro-sized devices and components. Interestingly, this very size-dependent nature can be used to obtain some novel devices which were not imagined earlier. For example, a single electron transistor is a completely new device due to unique properties of quantum dots. Magnetic spin valve and magnetic tunnel junction using nanomaterials are some other high-speed devices which are the product of nanotechnology. Let us discuss the tunnel magnetoresistance known as TMR. A schematic of a tunnel magnetoresistance has been shown clearly in the figure. Tunnel magnetoresistance TMR is a magnetoresistive effect that occurs in a magnetic tunnel junction, which is a component consisting of two ferromagnets separated by a thin insulator. If the insulating layer is thin enough, typically a few nanometer, electron can tunnel from one ferromagnet into the other. Since this process is forbidden in classical physics, the tunnel magnetoresistance is a strictly quantum mechanical phenomena. Magnetic tunnel junction are manufactured in thin film technology. On an industrial scale, the film deposition is done by magnetron sputter deposition. On a laboratory scale, molecular beam epitaxy or the pulse laser deposition. It is also possible by electron beam physical vapor deposition. The junctions are prepared by photolithography. Let us learn the basic phenomena of MTJ. When electrons are tunneling between two ferromagnetic metals, the magnitude of the tunneling current depends on the relative orientation of the magnetization of both electrodes. This can be understood from a few elementary arguments. The tunneling current is the first order proportional to the product of electrode density of state at the Fermi level. In ferromagnetic material, the ground state energy band in the vicinity of Fermi level are shifted in energy, yielding separate majority and minority bands for electron with opposite spin. And assuming a spin conservation for the tunneling electrons, there are two parallel currents of a spin up and a spin down character. As a result, these aspects, the current between electrodes with the same magnetization direction should be higher than those with the opposite magnetization. Let us discuss magnetic tunnel junction. Figure illustrates the mechanism of MTJ when the magnetization is parallel and below when the magnetization is anti-parallel, leading to reduction of total tunneling current. An important aspect for the presence of TMR is the ability to independently manipulate the direction of magnetization of the electrodes. This can be accomplished by several methods, which include or sometimes combined use of intrinsic differences in magnetic hysteresis of ferromagnetic material, exchange biasing and antiferromagnetic thin film and antiferromagnetic interlayer coupling across non-magnetic metallic film. The room temperature resistance changes for a MJT with a MgO barrier. Two soft magnetic cobalt iron boron electrode with different coercivity are used to create a clear distinction between the resistance level in parallel and anti-parallel alignment of magnetization. The change in resistance between anti-parallel and parallel magnetization normalized to a parallel resistance is given by TMR equal to 2P1P2 by 1 minus P1P2, where P1, 2 is equal to N1, 2 maximum minus N1, 2 minimum divided by N1, 2 maximum plus N1, 2 minimum, where P1, P2 are the so-called tunneling spin polarization determined by the relative difference in density of state at the Fermi level. It is crucial to realize that not all electrons present at the Fermi level can efficiently tunnel through the barrier, and that this simple equation is not able to capture the physics behind a number of observations in MTJ. In many cases, spherically symmetric S-like electrons, which have a much lower density of state at the Fermi level, dominantly tunnel through the barrier, and the interface between the insulating tunnel barrier and the ferromagnets plays an essential role. Nevertheless, this expression clearly demonstrates the presence of magnetoresistance effect and the relevance of the magnetic character for the spin polarization of the tunneling electrons. Moreover, it shows that so-called half-metallic metal with only one of the two spin species available at Fermi level, in principle, engender infinity high TMR. Indications for such behavior are indeed observed. For instance, in La2 by 3 SR1 by 3 MnO3 oblique SRTiO3 La2 by 3 SR1 by 3 MnO3 SR layers and CO2 FeL 0.5 Si 0.5. These are the few examples where we have seen this behavior predominantly. Let us discuss additional layers. Inserting an additional layer at the barrier ferromagnet interface has been investigated to rigorously probe the origin of tunneling spin polarization, shown so that inserting one monolayer of copper between the bottom cobalt electrode and the Al2O3 barrier lead to a strong reduction of TMR. USA et al. In 2002 have further developed these experiments by achieving SAR interfaces between single crystalline CO001 and copper 001 using molecular beam epitaxy. They explain that majority electrons tunneling from NiFe into cobalt would transmit easily as compared to minority electrons, which have a higher probability to be reflected at the copper cobalt interface. If multiple scattering occurs between cobalt, copper and copper-alumina interfaces, the minority electrons would form resonant quantum well state in copper layer, resulting in the accelerative behavior of TMR. Although most ferromagnets display a positive P in conjunction with Al2O3, Kasser et al. Have reported that cobalt-gadolinium alloy can exist both positive and negative P symmetrically depending on the alloy composition. It is known that in these alloys the cobalt and gadolinium ferromagnetic subnetwork magnetization is aligned anti-parallel with respect to each other, which may significantly influence the tunneling spin polarization. Now, the spin of P depends on orientation of the respective subnetwork magnetization with respect to applied field. The P from either of these subnetwork will be positive when its magnetization is aligned with the applied magnetic field, in contrast to the moment of the other subnetwork. Kasser et al. Found that the measured P is the sum of independent spin polarized tunneling current from the cobalt and gadolinium subnetworks, resulting in a spin change of P with alloys composition when combined with traditional ferromagnetic material with positive P in an MTJ. This leads to positive or negative TMR depending on the sign of cobalt-gadolinium polarization. Let us discuss coherent spin tunneling. The demagnetic sketch of the diffraction process where the incident electron is spin up has been shown in figure. One aspect which is highly unlikely in tunneling through an amorphous barrier is K conservation of electron wave vector. On the contrary, in a crystalline barrier, K conservation, also known as coherent tunneling, is a distinct possibility. This also implies that a wave vector selected at one interface efficiently coupled to a corresponding wave vector at the other interface. Keeping in mind that P is not constant over the whole Fermi surface, one could imagine that using a certain electrode barrier interface in a certain crystallographic orientation, which would result in efficient electron tunneling for wave function and which also have specific symmetries. This in turn could lead to a very large tunneling spin polarization, even though the average density of state at the Fermi level of the ferromagnet is only moderately polarized. Let us talk the future perspective. In the field of spintronics, MTJ display magnetoresistance effect due to the spin dependence of the tunneling current when dealing with ferromagnetic electrodes. The physics behind TMR has been experimentally and theoretically explored by introducing novel concepts and engineered material combinations. This has dramatically increased our knowledge of tunneling between ferromagnetic material. One can also see the giant magnetoresistance, half magnetic magnetism, magnetic recording system, spin electronics, magnetic recording system, spin walls, magnetoresistive head, magnetic tunnel transistor, multi-layer layers. In multi-layers we can discuss interlayer coupling, spin polarized scanning tunneling microscopy. So student, let us now summarize what you have learned in this module. The first one is magnetic tunnel junction (MTJ) are nanostructured devices within the field of magnetoelectronics or spintronics, hereafter called spintronics. The tunnel magnetoresistance (TMR) is a magnetoresistive effect that occurs in a magnetic tunnel junction, which is a component consisting of two ferromagnets separated by a thin insulator. If the insulating layer is thin enough, typically a few nanometer, electron can tunnel from one ferromagnet into the other. Since this process is forbidden in classical physics, the tunnel magnetoresistance is a strictly quantum mechanical phenomena. An important aspect for the presence of TMR is the ability to independently manipulate the direction of the magnetization of the electrodes. This can be accomplished by several methods, which include the sometimes combined use of intrinsic differences in magnetic hysteresis of the ferromagnetic materials, exchange biasing with antiferromagnetic thin films, and antiferromagnetic interlayer coupling across non-magnetic metallic films. Inserting an additional layer at the barrier ferromagnet interface has been investigated to rigorously probe the origin of tunneling spin polarization. In the field of spintronics, MTJ display magnetoresistance effect due to the spin dependence of the tunneling current when dealing with ferromagnetic electrodes. The physics behind TMR has been experimentally and theoretically explored by introducing novel concept and engineered material combinations. This has dramatically increased our knowledge of tunneling between ferromagnetic material. This is all about TMJ. Thank you very much.